Hi folks, I'm Dr. Ganesh. This is a series where I am trying to share my knowledge on machine learning. So we were seeing different steps in machine learning, starting from getting data, gathering data to pre-processing, and then selecting the right machine learning algorithm. And today we are going to see how do we gain insights from the model's results. Essentially, how do we evaluate a model? And in the next video, we will see the data visualization, transforming results into visuals. So, gaining insights from the model's results. There are a lot of evaluation metrics associated with machine learning. Some of them are specific to certain type of algorithms. For example, maybe accuracy makes more sense for classification, and it is used for classification problem where the output can be of two or more types of classes. Let's say we are solving a classification problem where we are predicting whether a person is having cancer or not. Let's give a label of 0 or 1 to our target variable. Say 1 is when the person is having cancer, 0 is when the person is not having cancer. The confusion matrix gives you 4 things. The true positives and the true negatives are the first part. So true positives are the cases when the actual class of the data point was 1 and the predicted is also 1. Example, the case where a person is actually having cancer and the model classifying his case as cancer comes under true positive. On the other side, true negative is nothing but when the actual class of data point is false and the predicted is also false. The case where a person not having cancer is actually predicted by the model as a person who has no cancer. And on the other hand, there are false positives and false negatives. False positives are the cases when actual class of the data point was 0 and the predicted value is 1. False is because the model has predicted incorrectly, and positive because the class predicted was a positive one. A person does not have a cancer, but the model predicted that person has cancer. That is really false positive. And now you can guess what is false negative means. False negatives are the cases when the actual class of the data point was 1, true, and predicted as 0. Someone has a cancer, but your model says no, he's all right. Very dangerous, isn't it? So the ideal scenario is that we all want is that the model should give 0 false positives and 0 false negatives. But in a real case, that will not be the case. We will have some false positives and some false negatives. Our aim is to evaluate how much of that is present and see if we can minimize. Let's say in our cancer detection problem, example, out of 100 people, only 5 people have cancer. In this case, we want to correctly classify all the cancerous persons, as even a very bad model will give us a 95% accuracy. But in order to capture all cancer cases, we might end up making a classification when the person actually not having cancer is classified as cancer. This might be okay because it is less dangerous than not identifying a cancerous patient. Because if the model says this person has cancer, we will not blindly believe. We will do tests, examinations, and that may say that okay, that was a false positive. Don't worry, you don't have cancer. But missing a cancer patient will be a huge mistake because we may not do further examination. So consider a model to classify an email as spam or not. Let's say that you are expecting an important email on a job offer. Let's say assign 1 as email is a spam, 0 as email is not spam. Suppose the model identifies that important email that you were desperately waiting for as spam. Now, in this situation, this is pretty bad that classifying a spam email as important or not spam, since in that case we can still go ahead and manually delete it. So in case of spam classification, minimizing false positive is more important than false negative. Whereas in that cancer detection, false negatives were more important. We wanted to minimize false negatives. Now let's see what all we can calculate with our confusion matrix. The most common evaluation metric that you might have heard of is accuracy. Accuracy is a good measure when the target variable classes in the data are nearly balanced. Example, 60% classes in our fruits images data are apple and 40% are oranges. The model predicts whether a new image is apple or an orange. 97% times correctly is a very good measure of this example. Now, how do you calculate accuracy? See here, accuracy is nothing but the sum of true positives and true negatives over the total number of values, sum of everything. So in an ideal world, if everything is true positive or true negative, accuracy is 100%. Accuracy should never be used as a measure when the target variable classes in the data are a majority of one class. So for example, take our cancer detection where dataset had only 5 people cancer and 95 people no cancer. Let's say our model is very bad and predicts every case as no cancer. It has still classified 95 non-cancerous patients correctly. Is that a good model? The number looks like 95% accuracy. But it may not be a good model because it doesn't work at all. It simply classifies everyone as no cancer. So a high accuracy does not mean it is correct unless you have balanced amount of data in your data set. Now another measure is precision. Precision measures that tells us is a measure that tells us what proportion of patients that was diagnosed as cancer actually had cancer. So the predicted it is the sum of true positives over the sum of true positives and false positives. So since we are predicting everyone as having cancer in our previous example, our denominator will be 100 and numerator will be 5. So the precision is only 5%, and that is really reflecting that algorithm is bad. Another measure is recall or sensitivity. Recall is a measure that tells us what proportion of patients that actually had cancer was diagnosed by the algorithm as having cancer. Example, in our cancer example with 100 people, 5 people actually have cancer. Let's say that the model predicts every case as cancer. So our denominator is 5, true positives and true false negatives. And numerator, person having cancer and the model also predicting as cancer is 5. So the recall of such model is 100%. We don't really want to have multiple parameters representing a particular algorithm. For example, can we get something predicted which says about both precision and recall? And F1 score is exactly doing that. Suppose we have 100 credit card transactions of which 97 are legit and 3 are fraud, and let's say we come up with a model that predicts everything as fraud. Suppose that we have 100 credit card transactions, 97 are legit and 3 are fraud. If we simply take arithmetic mean of both, then it comes out to be nearly 5%, 51%. We shouldn't be giving such a model score to a terrible model since it is just predicting everything as transaction as fraud. So we need something more balanced than arithmetic mean, and that is harmonic mean. So whereas arithmetic means comes in the middle, harmonic mean is slightly closer to that imbalanced value. So it's a kind of an average when x and y are equal, but when x and y are different, it is closer to the smaller number, and that gives a better idea. So in this example, when we calculate F1 score, the harmonic mean, which is 2 times precision recall divided by precision plus recall, it comes to 5% because your precision is only 3%. So this F1 score gives a sort of a combined outcome of how precision and recall works. So to summarize about confusion matrix, it's an n by n matrix. N is number of classes being predicted for the problem in hand. We have n equal to 2 and hence we get a 2 by 2 matrix. Accuracy, the proportion of total number of predictions that were correct. Precision, the proportion of positive cases that were correctly identified. And negative predictive value, proportion of negative cases that were correctly identified. Sensitivity or recall, proportion of actual positive cases which are correctly identified. And specificity, the proportion of actual negative cases which are correctly identified. So given a confusion matrix, you are able to go and calculate all these values from a single go. Now, if you take a regression model, root mean square error is one of the very commonly used measure to identify how your model performs. It does this by measuring difference between predicted values and actual values. Let's say you feed a model some input x and your model predicts 10, but the actual value is 5. The difference between your prediction and the actual value is the error. And why error is important? Because we want to minimize the error. So the root mean square error is calculated as sum of predicted minus actual the whole square over n and root of that. So in a good model, the root mean square error should be close for both your testing data and your training data. If your testing data gives you a higher root mean square error than training data, there's a high chance that your model is overfit. In other words, your model performed worse during testing, but it was okay during training. With that, let me thank you, and we'll see more metrics as we discuss specific algorithms and types of algorithms.